These ones are probably a little bit more important, okay? So here we have the dimensions of a rectangular box are given. Find the length of the diagonal of the solid, okay? So here are the dimensions right here. Okay, so again, we haven't really dealt with rectangular boxes or solids so far yet, but the big thing about solids, right, and prisms, rectangular prisms here like this, is that they have, right, a height, okay? They have a width, and they have a depth to them. Okay, that's why this is considered a three-dimensional figure here, because it has a height, right, of 5, a width of 5, and then a depth of 2. And that's how we're going to solve this problem. Okay, and in this one here, you want to find the length of the diagonal of the solid. Okay, so this is a little bit confusing because we've seen diagonals of quadrilaterals, right? This would be diagonal of quadrilaterals. This would be a diagonal of quadrilateral. That would be a diagonal of a quadrilateral. But a diagonal of a solid is a little bit more harder to see. So that's going actually through the solid itself. Okay, it goes from one corner of the solid through within the solid to another face to another corner. It's going to be considered a solid, the diagonal of the solid. Okay, so that's D here. We need to figure out what D is. It'll be flowing on the street. Okay. So looking at this, I might just redraw this diagram because it might appear a little confusing the first time around. So let's redraw this. Sometimes it's hard. Right now. Sing yourself out of depression, rise above. Okay, so that's my drawing of the actual rectangle itself. Okay, again, we know that the height is 5, the width is 5, and it has depth is 2 units. Okay, the way to solve a problem like this, our goal is to find the diagonal from one corner on top to this opposite corner down here on the other plane down below, right? Top plane and bottom plane across, connecting these two side planes right here. Okay, so that's our diagonal. Okay, as of now, we don't have enough information to solve for this, okay? Because what we need to do is, we only really know one side of a triangle that would contain D. So look at this here. D here, right, is in an angle like this. So it's going to end up being a hypotenuse of a right triangle. We got to locate that right triangle so far, okay? So here, right, the triangle you need to concern yourself with is this one right here. Running across, right, across the rectangular solid. Okay, so if we drew it in like this, this would be a right angle right here. Then we'd have D, okay? And then what will we know about this height? Well, we know this height from earlier in the problem, and this is 5. Okay, so this is 5 right here. That's D. And then the question is, well, this other leg, we don't know what that is yet. Is there a way we can figure that out? And it turns out we can, right? We can because we know that this here, right, remember it's a rectangular solid, so we know that all these angles are right angles, right? That would be a right angle there, that would be a right angle there, that would be a right angle there, but this is definitely a right angle there, and that's the thing we care about. That if we see the bottom of this is length 5, would be length 2, because remember we have a depth of 2 right here, okay? So then the question is, this A right here, this would be a diagonal of the base of this box, okay? So the first step in this problem right here would be to solve for that diagonal of this quadrilateral, okay? And then that's gonna help us get D, because then we would know 2 sides of this triangle, right, that would get formed with that diagonal in this plane traveling corner to corner through the box, okay? So in order to get A, we're gonna use, you guessed it, the Pythagorean theorem, okay? So A squared, right, that's the hypotenuse of this right triangle, equals 2 squared plus 5 squared, okay? So A squared is gonna equal 2 squared is 4, 5 squared is 25, A squared is gonna equal 29, take the square root of both sides, A would equal radical 29, okay? No perfect squares are gonna go into that, right? 9 does not go into that, and right, that would be the only odd perfect square. Well, I guess 25 would be another odd perfect square, but neither of those, lower than 29, but neither of those go into 29. So root 29 is the most we can simplify that right there. Okay, so now we know that A is root 29, right? That means we can solve for D because we have root 29 here, we have 5 there. Okay, D again is the hypotenuse of this triangle. So we're going to do D squared equal to 5 squared plus root 29 squared. D squared equals 25 plus 29. Okay, right? 5 squared is 29, root 29 squared. Well, those are inverse operations to the 29. So the 2 would cancel out the root. And then we would get 54 right here. Okay, so we will take the square root of both sides. This will be we'll be able to reduce this one. Okay, fun fact, which you may have heard before, that if the digits in a number actually add up to 9, then that means that number is divisible by 9. Okay, I know you all know that 54 is divisible by 9, right, some of the lot bigger numbers, right, that it goes for bigger numbers, in the hundreds, thousands, millions, the digits add up to 9 will be divisible. Okay, so let's go ahead and let's divide this by 9 and we get 6. Okay, so the reason that's important is because we can rewrite 54 in terms of its factors, right, 9 times 6. Okay, what do we know about 9? It's a perfect square. Right, is that perfect square, right? 9 square root of 9 equals 3, and we're left with 3 out of the 6. And that's our answer for D, which is what we were asked for, the length of the diagonal of the solid. Okay? Final question is number 28. Okay? Number 28 is the same thing here, so we still have a rectangular box, and our dimensions are given. Okay, so we'll make that the height. We'll make this the width, and we'll make this the so this here, I'm going to redraw this into diagram. This is too much for us. But the important thing, actually, one thing to note here is that these would all E, right? That's just a variable, right? But it's the same variable for all 3 dimensions. So in fact, this will be a cube, right? Rectangular box that will have the same height, width, and depth would actually be a cube. That is, it would have all equal edges. Okay, so I'm going to draw this down here. Height is E, width is E. Okay, so this will be the front face. It's a square. And then depth is going to be E. And I'll draw the rest. Dash lines for the parts. It'll be flowing on the street here. Night after night. Okay. So again, our goal is to find the diagonal of the solid, not a diagonal of the face, right? So we're not looking for the diagonal. So we needed one of the diagonals of the face to get the diagonal of the solid, but this diagonal of the solid is the thing that runs through the solid itself. Okay, it runs through one corner. Okay, not to the corner in the same plane. The same face of the cube, but actually through the cube itself. Okay, so from this corner through the cube, diagonally across the cube, and this is going to be the D we're going to find. Okay, again, this forms a right triangle. Here, I'm going to make it a little bit, I'm going to shade it in a little bit darker, the right triangle that we really care about getting D. Okay, there, and then again, this is D right here. I'll just make that shaded. Okay, hard to see angle-wise, but remember, this would have to be a right angle. This plane, it's these 2 planes, right, at a right angle at the bottom. Okay, so that means that this needs to be a right angle right here. A right angle right here. What do we know about this leg? Well, it's E, right? That's the height of the cube, okay? Do you know anything about this diagonal yet? We haven't solved for it yet, but we can solve for it really easily, okay? So again, depth is E, so this here would be a right angle, and therefore this would be a right triangle. That's going to help us get this. This would have to be the hypotenuse, the opposite, a right angle in this triangle. Okay? Use Pythagorean theorem to solve for what A is, and then the variable A is just something they choose randomly for this diagonal of one of the faces of the actual solid. Not the diagonal of the solid itself, but one of the faces of the surfaces. Okay? So let's get it. Pythagorean theorem, A squared equals, well, our 2 dimensions. sunshine, work it out. And A is going to equal, well, square root 2, we can't simplify that at all, right? So we'll get a square root of 2, but we can simplify E squared, right? E squared is a perfect square, the square root of E squared, well, that just gets rid of the squaring function. We're left with E in front, okay? So A here, right, is equal to E root 2. Okay, and that's helpful, right? Because now we have E root 2, we have E right here. We can use these variables here to at least come up with some sort of simplified expression in terms of E, solving for D, right? The diagonal of the solid, okay? Again, diagonal of the solid is the hypotenuse of this right triangle, okay? And so we'll plug in what we know about these lengths in terms of E, right? In terms of E. So D squared, which is what we're looking to find finally, is going to equal the sum of these two legs. So the sum of the squares of these two legs. So E squared plus, right, the square E root 2 squared. Okay, that leg squared is this, that leg squared is that. Okay, so let's go ahead and simplify this and solve for D. D squared equals E squared, and then, right, this one again would get us another E squared times by 2 this time, right? Root 2 squared is just going to be 2. And then we're going to get, after we combine some like terms here, well, this would be 2e squared plus another e squared. That's 3e squared. Okay? And to solve for D, the diagonal, last but certainly not least, we need to get rid of that squaring there. So let's root both sides to simplify, to isolate D, and then we'll be good to go, right? Square root's going to cancel out the squaring of the e. Again, this does not go to the 3. This is the coefficient of this exponential expression right there. So e squared will simplify to just e, but root 3 will have to remain as root 3, okay? And that solves it for us here. All right, pretty tricky problems. We won't really have to deal with solids quite like this until chapter 10, but they wanted to give us a preview and show us an application of this using the Pythagorean theorem. Hope you had fun. Thanks again for the parking lot questions. Feel free to ask for these anytime. Have a good one.
Shockwave central power on the motherboard, yes. Push up, overload, legendary heavy glow, sunshine, thunder roll, keep this on. Yes, the lantern burn, bad easy, and broadcast so raw and easy. Thunder roll, sunshine, work it out.